Welcome, this is the AP Physics Workbooks tutorial. This is Unit 4, Work and Energy. The section is 4.0, Conservation of Energy and Circular Motion. Yeah, you could read the scenario to yourself. But what I wanted to explain to you is that notice as it comes down here, this should remind you of a conservation of energy problem. So it's going to start here, it's going to come down here, and it's going to go to this point. At this point here at Q, here it's going to have both kinetic energy and potential energy. The reason why is because it gets the kinetic from here, it's all U. This it's going to be transformed into kinetic and U. This energy, there's going to be a velocity this way. So remember, there is a tangential velocity going there, but there's also a centripetal acceleration that goes towards the center, because remember, this is a circular object. If the velocity is greater than the force centripetal, it's going to fly out of the track basically. So that's what they're asking here. Right, so the first question asks, what is the speed of the cart when it is on top of the Neptune sphere? So it's on top here. We're looking for V. So we're going to use our conservation of energy. Okay, so all the potential here, it's going to be equal to kinetic and potential here. All right, let's see that. All right, so the first thing I want to mention is that the system is closed and based on conservation of energy. We can say that the energy on top of Jupiter is going to be equal to the energy on top of Neptune. On top of Jupiter, you have the potential energy on top of Jupiter plus the kinetic energy on top of Jupiter. That's going to be equal to potential on top of Neptune and the kinetic on top of Neptune. But here's the difference. Remember, the kinetic of Jupiter, hold on, give me a second. Yeah, so I made a mistake. It's not the kinetic of Jupiter. The kinetic of Jupiter goes to 0, right? What's left is the potential. So that is mgh, okay? So I flipped this. I'm going to come back and change it, right? So you have the potential mgh, and the h here is 2r. That's going to be equal to the potential here on top of Neptune, which is mgh, and for here the radius is r, so the height is 2r, and the kinetic energy, which is just 1/2 mv squared. Notice that the velocity at the top of Neptune will have the kinetic energy on top of Jupiter, will have the kinetic energy on top of Jupiter minus the potential energy on top of Neptune. All right, so that is not correct. All right, so this is wrong. It should be potential. All right, so the kinetic, this goes to 0. Because it starts from rest. So this goes to 0. Right? So it leaves you this. And how I got that is that this is R, this is R. So the whole thing here would be 2R. Hopefully you could see that. Here, let me go blue. Here, down here is R, so it goes up here, which is also R. The whole thing would be 2R, right? The diameter would be 2R. Same thing here. The diameter would be 2 little r. All right? Then we would say that down here, the velocity is going to, at the end, on top of Neptune, we'll have the kinetic energy. No, we'll have the, not the kinetic energy, we'll have the potential energy from on top of Jupiter minus the potential energy on top of Neptune. Yeah, that is correct. Let's see that. So it's gonna have, you're gonna have this. So here, let me show you here. If you want to see that using this equation, look. Right, so the 0 goes away. Right, you're gonna subtract the Neptune here. So it's going to be U of Jupiter minus U of Neptune. That's going to be That's going to be equal to the kinetic energy of Neptune, right? And that's how it should look like. Okay, and it's going to be a subtraction. And if you want to write that, it should look like mg2r minus this. So mg2 big R minus mg2 little r, that's going to be equal to 1/2 mv squared. There you go. Okay, so the velocity right here is going to be dependent on that. All right, good. Now we can take a look at looking at the equation for it. All right, so on the AP Physics exam, you would say that the system is closed because there is no net force exerting on it. This allows you to use conservation of energy. So, like I have this equation from before, I have it from above. Now all I did is the mass cancels, so this is what you're left with. Conservation of energy does not depend on mass. I then factored out the 2 from both. So I multiplied the 2 here to get v squared alone. Then I square root both sides. Once I square root both sides, I know the square root of 4 becomes 2. So I get this answer. V is equal to 2 square root g parentheses r minus r. Right? Now we want to look at the normal force on top of Neptune's sphere. So we have to do centripetal force here. Okay? All right. Let me just bring this down so we can just see it a little bit more. All right. Okay. All right. It's a long deviation, okay? So bear with me. All right? So you have the summation of force centripetal is going to be equal to Fg minus Fn. Why? Because here it goes up, which is going to be force normal. Going down would be Fg. So it's Fn minus Fg. All right. Then this becomes MAC is equal to Fg minus Fn. Right? Because this is the definition of centripetal, the centripetal force. Okay? Mass times the centripetal acceleration. Let's solve for Fn. So what can I do here? Oh, you know what? I'm going to put Fn on this side, right? I'm going to add Fn to both sides. Add Fn to both sides. Then I'm going to subtract MAC. Subtract MAC. So it should look like this as the next line. Fn is equal to Fg minus MAC. All right. Then we want to, let's see here. Oh, force of gravity is just mg minus MAC. So you can factor out an m. So you have just g minus AC. Do we know what AC is? Okay. We know that AC is equal to v squared over r. So g minus, do we know what v is? Yes, we do. It's right here. Boom. We can put that here, but be very careful. You got to square this, and this is going to be over r. So that looks like, this is ugly. G minus, let's see, 4g r, big R minus little r over r here. Perfect. All right. Yep, there you go. And this is still in the parentheses. All right. Give me a second to give us more room. Okay. Then let's see. All right, let's see. I need to get Fn in terms of something, so I have to clean this up. And remember, this is equal to Fn, right? So, all right, these are all, Fn is still on the left side, but I haven't been writing it. Okay. All right, let's see. Then we have, let's just distribute. So here you have G minus 4G big R divided by little r plus, because this is a minus, 4G little r over r. Okay, hopefully you see the distribution. Okay, I distributed this to both terms, okay, to get this line. All right, so more things canceled out. Mg minus 4G big R over little r plus 4G, because here, you know, these cancel. All right. Then we have Fn is going to be equal to Mg minus, let's see. Oh, we have G plus 4G. So this becomes 5G minus 4GR over R. So what I did is these two were like terms. So I added that. All right. So Fn is equal to M 5G minus 4G big R little r over. Okay, and then let's see, what else can we do here? Oh, there's a G in both things, so I could factor out a G. So M, so G, right? Mg. What's left is 5 minus 4 r little r here, right? So again, why? Because take a look, G here, G here. That's why I was allowed to factor it out. So this force normal is equal to mass gravity times this weird radius difference. Okay, that's what this is. You've seen mg times r before. Okay, the only difference here is because there's this whole, you know, velocity that you get from here. It behaves a little bit more weird, but the equation should still be normal. Okay, you should still be comfortable with this. All right, that's the deviation for you. Whew, that was big. That was weird. So if you want to see it in its full form, hopefully you can see it like there. Yeah, that's basically it if you want the short version. Okay, hopefully you can make sense of this. All right, so let's see. Select a part to support the engineer's reason. Engineer B said that if the height difference between the top of Jupiter and the top of Neptune is too much, the car would go fast at point Q, causing the car to lose contact with the track. And we see this equation right here. Okay, that's where we see it. That was the velocity equation. And we saw that r minus r is the height difference. So as r minus r increase, the velocity will also be squared. So if r minus r is doubled, then the velocity will be quadrupled. Right? So this proves that if the height difference, again, this is the definition of height difference, here is too much. That is what we mean by doubled, right? Right here, if it's too much, if r2 is doubled, okay, we see that the velocity will be quadrupled. And if it's going to quadruple, it's going to fall off the track. Let's look at what engineer C said. So engineer C said that no, it is not the difference between the height that is the problem, but the small radius of the curvature of the track as it goes over Neptune. So I selected mg minus mv squared over r equals to fn. That was, let's see, this step right here. All right. So hold on, where was it? Yeah, mg v squared over r. That's where I made the substitution. So I basically did this step right here. Okay. But you just had to plug in v squared over r here. Right? I saw that if I let r approaches negative infinity, okay, because it goes extremely small to the point that it goes towards negative infinity. If that goes to negative infinity, then this whole term of mv squared over r will become a large negative number. Okay, because this becomes towards negative infinity. Okay, this will become a super negative number to the point that now you get an mg minus a negative term, a negative, right? A minus a negative term, which means you just add that term. So here you would say that the normal force will be greater than the force holding it down. Therefore, the car will lose contact with the track, right? That is only because this goes to an extremely negative number, making this flip to become positive. And if you add these two, you will see that if the normal force is not as great, it cannot hold the cart down, right? You're going to see it when I do the math here to see what combination of like which planet, which radius would be good here for for the second ride. Okay, we notice that this radius of Neptune is problematic of 0.35. We'll see which one would be good for it. There are three scenarios that you should take a look at. One, if it's equal, right? This is the equation that I've just used from before, right? I just used the last part here, mg 5 minus 4r, 4 big R little r. I use that. If I see if that's equal, the object is going to stay on the track. Okay, the centripetal acceleration balances out. But if that is larger than Fn, it's still going to stay on the track. But if Fn is larger than the force holding it down, the object will fly off the track. Now, so we're going to take a look at the math when the object still stays on the track. So mg 5 minus 4 big R little r has to be greater than or equal to that. I'm referring to this part. Okay? All right. So I distribute mg over. Then I add mg to the other side to look like that. Okay. The mg's cancel. I could solve for little r because the little r is the radius of the second track. And I saw that little r has to be greater than or equal to 4 big R over 5. R is the radius of Jupiter and R is the second planet's radius. So the second ride's radius has to be greater than or equal to 1/5 of Jupiter's radius. And the only thing that works for that would be Saturn. All right, but here's the deviation if you want to see it. Okay, there you go. That's everything that you need to know about 4.0.